So are you able to see the PPT? So are you able to see the shared material? So today, see, it is basically the new topic, wave radar based detection systems, right? See, I want to tell you that what I have learned basically the fundamentals of the digital signal processing, thereafter the graph signal processing, but initially also the biomedical signal that my student Suman helped me to learn. And now it is another topic, wave radar, that we are basically doing a project given by the Ministry of Electronics and Information Technology, METI. And here my student Anand actually, he is working and there I am learning. So it is basically not my direct learning, but actually again the indirect learning along with my student. So we started basically that work from the year 2023 and it is our almost 2 years we have completed. So remember in this topic, wave radar, it is millimeter wave radar. So you would see that when the people are talking about the automatic vehicles, right? Automatic vehicle, automatic cars, which are there, which automatically control the speed, which detects the person, etc. All these things are there that are basically based upon this concept, right? MMA. So how does it help? It's a very new technology. What we are doing in the project, basically we are making a different algorithm which can work out uh, for the different purposes, and then we want to encode in a chip. It's a basically collaborative project along with Triple IT Hyderabad and the Aligarh Muslim University. There we are working. So it's almost a very new technology. It's a hardware. So introduction, it is basically to the wave radar. Why millimeter wave radar? What is this thing? See, you would have been knowing this is radar is basically something just in the India-Pakistan war, you would have noticed that word many times. Radar is basically something which detects some incoming signal. For example, if some missile is coming, right? Some missile is coming from the Pakistan, and you have to not only detect it, but also you have to respond it back so that you can stop it at the right time. So that is basically the radar which sends it. Even see, I am happy to tell you that my first job in the Central Research Lab, BEL Bharat Electronics Limited, that primarily works to develop the radar. So that way, BEL Bharat Electronics Limited indigenously developed the radar components and design the radar. It is one of the Navratna company located in the Ghaziabad and the Bangalore. So what we are saying, millimeter wave radar operates in the frequency range of 30 gigahertz to 300 gigahertz, typically using bands like 24 gigahertz, 60 gigahertz, 77 gigahertz, and 79 gigahertz. See, so why we are talking about this range, why this range is that much important. See, this range is important because, see, any idea? You are basically faculty, senior research students. Any idea that why do we consider this range? See, this is basically given by basically the antenna size. If you recall, see in our communication engineering when we have gone through it, that is C equal to F multiplied by lambda. When this is your frequency range is given, then what would be the size of the antenna? If you would have noticed that the size of the antenna is basically lambda by 10. So that antenna is very, very easy to design, right? That's why we prefer this frequency. It utilizes EM wave. As soon as we are talking about the antenna, see the primarily medium is basically the EM wave. With millimeter scale wavelengths to detect objects and measure their range, velocity, and angle. It is widely used in automotive, industrial, and security applications due to its robustness in various environments. So, when you see for example, so what does it do? It basically detects the, as we are saying that it detects the thing. Something detects the event like the camera. See, then you would have been thinking, see, already when camera is there, what is the problem with the camera? See, if you would have noticed, camera requires a good light. Can camera work in fog and smoke? No. What about the resolution? Resolution again, it needs to be the higher one. Is it, uh, doesn't it violate privacy? Yes, it violates the privacy many times. Many times I don't want the identity, but even see from the image, from the picture, it is your identity is revealed. So that is another problem. Another option in compared to camera, it is basically the infrared. In infrared light condition, it is low light. It is low light conditions are fine. But does it work in the fog and smoke? No. What is its resolution? It is moderate. Here it's a problem. Is it privacy friendly? Again, see there is a problem. Then we comes to the another important device, lidar. See, why are we lidar basically is good in light. Okay, but limited. Can it work in fog and smoke? No. Why fog and smoke matters? Because it matters because many times weather condition when you are driving your vehicle, these becomes the weather condition. Resolution, basically resolution high 3D. Is it privacy friendly? Yeah, it is conditional. Many times it is there, but many times it is not there. What about the MM wave radar? MM wave radar, no light condition. In any condition it will work. Can it work in fog and smoke? Yes, it can work. Resolution, it is high. You can easily get good one, good detail. By resolution, I means you can note the minute details, right? Whatever is happening in the background, sensitive thing. Is it privacy friendly? Yes, it is privacy friendly. So see, what do you notice? See, for example, in the bathrooms, etc., when there is a chances for the slip, the person can slip. There, these MMA radars are used, which basically which gives the alarm, etc. As soon as the person slips down or these type of things, where camera is not a desired. So overview of MMA radar technology. What has happened? See, radar basically consists of both the things. Not only consists of the receiver, but also it consists of the sender also. What we are saying, if you this is the block diagram is there, here mixer is here. Something is basically coming from the receiver antenna, which is coming. So a transmitter sends out frequency modulated chirp signal. The receiver captures the reflected signal from the target. See, how does basically MM radar sense? It sends continuously the signal. And when something is come back, then it is able to know that from what speed that object is coming. So that's why it is saying a receiver captures the reflected signal from the target that is there. So thereafter, signal generation definitely from the transmitted antenna. Since I produce the chirp signal used by the transmitted antenna, signal reflection, the chirp reflects off the target and returns to the receiver antenna. Signal processing, here it happens in mixer. It combines the transmitted and received signals to generate an intermediate signal. So intermediate signal is generated from which I am able to know that what is basically the received signal component. Integration, it is analog, its clocking mechanism provides synchronization, it is digital, it is ADC, MCU, and DSP handle digitization and signal processing. In CMOS technology, it is integrates both analog and digital circuits efficiently. So, what is the advantage of MM-wave radar in detection systems? MM-wave radar can penetrate materials such as clothing, plastic, and walls and are highly effective in detecting objects even through obstruction. This makes them particularly suitable for indoor monitoring, automotive applications, and scenarios where visibility is compromised. Unlike optical, so that's why it is there. Because it can penetrate walls. That's why it is effective. And unlike optical sensors, which are camera or radar, MM radar is unaffected by environment condition, as we have seen in the last table, fog, smoke, dust, or complete darkness. So this make it all weather prevalent. This ensures consistent performance across a wide range of challenging scenarios, enhancing safety and reliability, especially in autonomous system. What we are talking about basically autonomous vehicle or autonomous car or search and rescue operation. Modern MM-wave radar modules are compact and lightweight, making them ideal for integration into embedded system and edge devices such as drones, mobile robots, and wearables. This allows for flexible deployment in a space-constrained environment. So that we are saying basically as they are compact and lightweight, that's why they can be integrated into embedded system and the drones, mobile robots, and wearables. Since MM-wave radar does not rely on ambient light or illumination, it maintains stable performance regardless of lighting conditions. This robustness makes it more reliable than traditional vision-based system in dynamic or poorly lit environment. Now coming to the part that is basically the, is the slide visible easily or is better? The slide
Yes.
okay, thank you so much. Actually, it was not full screen. That's why I was thinking that should I do the full screen? Yes, thank you. So it is basically the road object detection. See, my simple message to the students see, who are working to get into the company or for the good publication. Remember, see, those students who have basically new to the research, see, pick up the topics, pick up the new topics. It is not necessary that where you need to the again image processing based topics, etc., etc. Whatever topic where you are interested in, where you are, see, once you are interested, then you can read lot of literature, and once you can read lot of literature, then you are able to emphasize upon these things while you are writing, as well as you will enjoy it. See, that's why these topics have a lot of potential. See, earlier, even see, I also share you very frankly that if project wouldn't be there, I wouldn't have approved this topic. But once we have approved this topic, it's very potential for the publication. Those students who have the option, they can definitely go to the new type of topic so that you can increase the publication. So now coming to the road object detection, it is essential for autonomous driving. Here, one term is used, ADAS, basically that Advanced Driver Assistance Systems, and improving overall road safety. Road object detection involves identifying and classifying objects like vehicles, pedestrians, traffic signs, and animals on or near roadways. See, you will also see in our work that how we are basically detecting the different objects from the with the help of the MM-wave radar. Common sensors include cameras, this is RGB, and infrared radar, MM-wave radar for 3D structure, and ultrasonic sensor for short range detection. Techniques range from traditional image processing and machine learning to advanced deep learning methods such as CNN, YOLO, SSD, and faster CNN. Even see SSD also is basically the deep learning technique. Sensor fusion is used to enhance reliability by combining data from multiple sensors. Major challenges in the row detection. Right. So you are using the data from the different sensors. Major challenges include adverse weather, poor lighting. Adverse weather, see, somehow even the effect is minimized, but still see while raining, etc., limitations are there. Poor lighting, even see lighting is not directly there, but somehow it is some effect is there. Varying object type and the need for real-time processing. So what we are saying, see, these are the challenges in a road object detection, in a normal road object detection. So here MM-wave radar is used to detect road objects such as vehicles, pedestrians, and obstacles by emitting high frequency electromagnetic waves. How much high frequency? That we have seen 30 gigahertz to 300 gigahertz, and analyzing their reflection. It provides accurate information on the distance, speed, and angle of road object, even in poor visibility conditions like fog, rain, or darkness. Road object detection using mmWave radar is robust in challenging environments where traditional vision-based sensors may fail. The radar generates point cloud data that represents the position and motion of road objects in 2D or 3D space. So please notice this term. See this one. See, as you are seeing here, this is point cloud data, right? Are you able to see? Radar generates point cloud data. Here is a key term that in image basically you process the data where pixels are generated, image is generated, but here it's a point cloud data that we will explore. That how is it? What is basically type of this point cloud data that represent the position. So now coming to the next one. So this is so now what we are doing. We are basically opening the different functionalities of the mmWave radar. So one is basically the road object detection. So what we have seen that the challenges of the road object detection are easily managed by using the mmWave radar. Now you see in reference to the literature work in description the what is showing here the challenges with camera based detection poor condition it is so this is shown here that we have already discussed that is robust detection using mmWave radar in adverse conditions. So that is radar-based object detection. It has been shown in this table. Improved classification using radar point clouds. So this can be helpful. So again here the mmWave radar is a point cloud classification. Target tracking using time series LSTM. LSTM when it has come. So what we are saying, it is basically the deep learning technique here. So this is another work object organization using range Doppler metrics. So here 79 gigahertz radar, it is RDM analysis. In another one, basically target separation via dictionary learning. Here, what we use is sparsity based dictionary learning. YOLO 3 on radar Doppler images. So here also radar is used. But remember one thing, see, as soon as we are going higher to this frequency, 79 gigahertz, they are not very easy to build. They are not very easy to operate. So first, it is better to design the radar which is working at the low frequency. So, for example, it may be the 50 gigahertz, it may be 30 gigahertz. So this type of thing. Hybrid detection using edge visual sensors and radar. So in radar type wave plus vision, so is a hybrid system. DNN classification using FMCW radar. So what is key technique here? DNN range angle heat map. Movement detection using DRNN and the Doppler fingerprint. So here also it is this one FMCW frequency modulated wave. So here also DRNN is used. This is road boundary detection is road and camera. Here it is camera plus wave. So here we can use basically the sensor fusion. Then MS YOLO for radar and vision. And here we are using key technique is MS YOLO. Evaluation with CRUW dataset. Here it is basically 3D localization annotation. Deep radar detection with frequency heat map. Here it is a range azimuth heat maps. Robust tracking via camera radar fusion. Here it is monocular plus radar fusion tracking. Pedestrians, cyclists, micro Doppler analysis. Here millimeter wave simulation study. So we finally want to do here, we adopt wave radar to enable the detection and classification of critical road elements such as vehicles, pedestrians, cyclists, and road boundaries, even in low visibility conditions. Enhance data representation to improve interpretability and facilitate processing. We apply a top view filtration technique to convert radar point cloud data into meaningful 2D representations. Please note it here that your radar point cloud data, that is basically the actual data that is converted into the meaningful 2D representations, right? So effective feature extraction. Now the question comes, once you have the data, point cloud data, what you are going to do with it? It's then simple. It is, we can also do the deep learning techniques also. Why? Because see, they are, if something is good, then it is utilized to extract robust features from the processed radar images, enhancing classification accuracy across object type. So that is the thing. Real-time embedded implementation. To validate our system in real-world scenarios, we implement the proposed multi-object detection and recognition pipeline in Ping JDU FPGA platform, offering a true embedded architecture with real-time performance and energy efficiency. So now what comes under the data pre-processing? Data pre-processing, initial raw data for each object was hardware setup for data collection. So now you can see that the how is basically the data is set. A radar setup was mounted on a tripod at a height of approximately 80 to 100 centimeter above the ground. So here you are seeing it again. It is the scene of the MN90 only. The radar was positioned 3 to 5 meters from the left and the right sides of the road. So you are seeing it basically 80 to 100 centimeters right, and it was positioned 3 to 5 meters from the left and right side of the road during experimentation. The overall system architecture is depicted in figure 2, outlining the complete data processing pipeline. Object recognition using radar. That was performed for 4 categories: cars, cyclists, pedestrians, and road boundaries at a distance of 10 to 20 meters. Object recognition was performed. So these were the basically categories. Here we also initiated experiment and we will share our result also later. How many samples? So this is how we collected these many samples. 1733. So this is saying boundary images are 293, car images are 480, cyclist images are 480, and pedestrian images are 480. So in the data pre-processing, what you are saying initially, raw data for each object was used to generate 3D point cloud images. Key point here, it is point cloud images. Top view filtering technique was then applied to convert the 3D point cloud data into a 2D point cloud images. So when we are processing, when we are going to process the algorithms, then we convert that 3D into the 2D without losing any information. So in the top view filtration, it simplifies the 3D radar data by projecting it onto the XY plane, effectively removing the Z coordinate while preserving the X and Y coordinate. This projection creates a 2D representation. See, when your 3D point cloud has been converted into 2D, that retains the spatial distribution of objects in the horizontal plane. The main advantage of this technique is easier visualization and analysis, especially for distant object detection. See, not only this time, but also when you are doing some mathematics and somehow you don't have access to the main data, then also you can perform. So now what is the hardware here? The PINC-ZU based implementation. PINC-ZU FPGA board was chosen for the real-time road object detection system. It outperformed boards like PINC-Z2. Is anyone aware about the PINC-ZU board? The PINC-ZU FPGA board was chosen for the real-time object detection using outperforming boards like PINC-Z. See, what are the use of these boards? Because they are already allow you to use your Python program, right? What because see another option VHDL. In VHDL you have to perform the whole uh, that language SDL language, but in PINC-ZU your Python your code in Python that is directly transported. PINC-ZU is built on the Zynq Ultra Scale plus MP system on chip, which integrates ARM Cortex A53 processor for general purpose tasks. So, what is this basically? PINC-ZU. PINC is again related from the Python. Right? ZU is basically the model. ARM Cortex R5 processor for real-time low latency operations. Programmable logic fabric for hardware acceleration. In contrast, PINC-Z2 uses this is the older version 7000 series SoC, which is fewer ARM cores, limited programmable logic, reduced capability for parallel processing and acceleration. So those people who are interested in doing basically the hardware, they would able to see these stuff, because today when you see even see you can write algorithm, but finally how much time does it require, right? How much time does it require to execute? How much resources is required? All these things can be checked in a real-time setting when you use basically these type of platforms. So you can see this board here. So what is this board here? Ping Z2 also lacks ease of integration for machine learning and hardware acceleration tasks. The road object detection application was tested on the Ping Z2 hardware platform, demonstrating it as a true embedded system design. So this is basically the workflow of object detection. Here input road object like car, bike, cyclist, pedestrian, road boundary. These are there. So what if see this is basically flow chart. So what is there here? Target road object is there. mmWave radar has captured it. So what it has basically converted into a 3D point cloud images, as we have already seen that this 3D point you convert into a 2D. So there are the two ways basically that you are the take the top view or the front view. Then you take the top view basically to take into account the information, key information. So and even in top view and front view, top view was found to be better. So thereafter it is feature extraction using VGG16 and then machine learning models are applied. Remember, once your data comes, as like in the image, basically in the form of pixels, it's a collection. Here it's in a 2D point cloud. That is again the key data. So from there you can feature extraction using VGG16. VGG basically, yes, here it's a deep learning. And thereafter machine learning models can be applied. So there we are able to know the hardware analysis for object detection and software analysis also for object detection. What will be the output? Output will be the classification like car, bike, cyclist, pedestrian, road boundary. So workflow of this object detection that has been so here we have also the one of our publications on this one. So what is it about? What is its overall summary? That the data set consists of 1,733 samples divided into 4 classes. Number of samples for each class is given in table 2. The data set was split into 2 subsets, 80% for training, 20% for testing. 4 machine learning models were evaluated for object detection, SVM, RF, DT, logistic regression. Performance wise, what you can see that the SVM and LR both achieved 97% accuracy in object detection. RF. So once we have the data, then there's this point cloud data.
Slide is not moving.
Sorry.
Stuck at ping chatting board.
Page ID board, see, just let me. Stuck in ping ID. Let's see, just a minute. You can check it now. So, are you able to see?
Yes, easy. Workflow, yes. Now move.
Right. So this is the thing here. See, my one question is there. Here, when we are applying it, BGG 16, so can't we apply direct? So what is the need of applying the deep learning and machine learning model together? Is it necessary? Those people who are working, this is my question regarding the implemented algorithm. Means are not we increasing the complexity unnecessarily? This is my question to everyone. So please try to think about it. Even see Anand is also, except Anand, I am asking everyone that what is the need of applying deep learning and machine learning together, because more or less we have seen them either machine learning or deep learning, but here it has both of them been applied. So except Anand, I am asking everyone that what is it utility? Results and discussion. Now see, when we come to the results and discussion, so the data set divided into four classes, number of samples for each class is detailed in table 2. What is table 2? So this is table 2 here. It is 80% for training, 20% for testing. It's the general rule. Even you 70-30 depends upon you. 4 machine learning models are evaluated for object detection. So this is the one, this is the simple one. Here performance results are there. So when you use basically the BJG16 and you LR, basically logistic regression, and then you use the SVM. So there, this is the result which is are good with top view filter. Without top view filter, it was with, means without top view means basically front view. So it is 95.9, and here it was a very good one when we use basically the logistic regression and SVM. What do you mean by the class? Class means basically how many uh, categories are there for the identification. Right. This is, if you see very carefully here, that we are comparing with the deep learning models, except this SV. So this is basically the confusion matrix. You would have observed. Let's see what do you mean by confusion. Confusion matrix means when boundary was there, it was rightly classified as 59% times. Car was classified as successfully as 84% time. So this is cyclist, 95, this is pedestrian. So can you see, really see here that boundary is not very easy to detect, because boundary has a very, very thin line, very limited features are there. That's why the boundary becomes a far difficult to identify in comparison to the cyclist and the pedestrian. Because in a pedestrian and a human being, see, it is not that difficult. Even in a car also, see, car also some problems are there. But in boundary part, which is itself narrow, it becomes a issue. In the future scope. So here what our proposal presents a hardware software approach for object detection and recognition around autonomous vehicles. The method is real-time and validated using a rapid prototype built on the FPGA platform. Field programmable gate array, so as you would have observed it, that this allows you to make your system as real-time, useful for chip design, etc. The research aims to assist human drivers in safely navigating adverse weather conditions, especially when vehicle vision and road boundary visibility are limited. Here, the system uses mmWave radar combined with several machine learning approaches to detect objects in various weather scenarios. While MM-wave radar performs well in low visibility environments, its accuracy can be degraded due to noise interference, signal attenuation caused by heavy rain or pollution. Definitely, that thing is not in our hand. Only we have to address it. To improve reliability, future focus should focus on overcoming these challenges by employing data fusion techniques such as integrating MM-wave radar data with camera in. Now see, we come to the in-vehicle occupancy detection using MM-wave radar. I tell you one story so you would understand its reality. Just before a few days, one of the child basically died in a car when in an automatic car. Those children were unable to open the lock, right? So this becomes the problem. This in-vehicle occupancy there it becomes very useful. What do we do here in vehicle that you are able to detect the person that who is there and how what is the case there. So MMA radar operates in the 77 to 79 gigahertz band and is used for in-vehicle occupancy detection due to its high resolution, robustness in various lighting conditions, and ability to penetrate materials like fabric and plastic. The main problem is accurately detecting and classifying occupants inside a vehicle, including children and adults, in real time and in optically challenging conditions while ensuring privacy and low power consumption. Additionally, camera-based systems are limited by lighting conditions and privacy concerns, and they often struggle with occlusion and thermal noise. As we already discussed, that this is the main problem with the camera. Infrared radar provides non-intrusive sensing by detecting reflected signals. Even if you are not only able to know that the how many persons are there, but where is he sitting, where he or she is sitting. So by detecting reflected signals from objects and movements based on range, velocity, and angle of arrival. The system typically consists of a radar sensor placed on the vehicle roof or uh, dashboard, a signal processing unit for cleaning and transforming raw data, and a classification unit for interpreting presence and type of documents. You see by the diagram that what happened. So related work has been shown as it has been uh, shown here that in MM-wave plus machine learning, it is effective for adult detection. It is challenge detecting newborns. Low cost MM-wave radar, improved monitoring performance, limited resolution, FMCW radar plus SVM plus Kaplan filtering, high accuracy in recognition. Misclassification, resolution constraint are there. These are the related work where you can compare. So this is the basically the scenario. Here you are seeing basically a car here, and here the person is detected in the this is in vehicle detection. In order to experiment for this research, FMCW radar, especially the Texas instruments, uh, booster pack evaluation board, which operates in the this range, was mounted on a tripod and placed between 30 and 40 centimeter above the floor of the car. In this experiment, 5 to 6 passengers were involved, and the radar module was connected via USB to PC for data processing. Right. So the carefully designed experiment set assist to assess the system in 6 different scenarios, all of which focus on determining vehicle occupancy. Even see when automatic cars are there, for example, in a group sharing car, somebody presses a buzzer. So even then automatic car, it would be known that which person wants to come out from the car. Here also its application. As shown in table, a total of 3070 samples were gathered in six distinct scenarios in order to determine vehicle occupancy. Where you see the beautiful thing I tell you with MMV radar that in a limited time you are able to generate the different type of many images. You would have been thinking that it would take much more time, but no, I think it hardly takes how much time we are able to calculate 3070 samples.
1 day to 3 days. 2 to 3 days.
There. But how much time did you
Uh,
sit regularly?
So, how to track?
For how much time you remained in the car to collect the thing?
Only 5 to 10 minutes.
So see, so that's what we are telling in the devices. See, earlier I was basically puzzled that so many samples were there in the literature review paper. But as Anand, I just asked him, so he told that around 10 to 15 minutes you in the car and that many samples were generated. Particular sample. So what is basically sampling? This is a very interesting coding. 00 means basically no person is there at the back seat. 100 means the person is basically the left hand seat. And then 010, it is the middle person is there. And this is the scenario when all the three persons are there. So the only my one message through this workshop, through this FDP program, that hardware things are generally we think, even I also thought during my college time that these were very difficult things. It took a lot of time. But I am telling you, please break that barrier. Because the hardware gives only actual real setting how the things are going to happen, and you have the edge that you are able to generate the data asset. So I'm telling you, even this is my beginning of the hardware only with this project. But I don't want that you people also, if you have the time, see, please pick up the hardware if it is if the option is there. It's a very, very good way to follow the DSP. Data pre-processing. In the data pre-processing, what we are saying here, that initially raw data for so that you are seeing here. So this is the case here that one person was there on the left hand side 010. So this is basically the point cloud. Are you able to observe? These green dots, etc., are there. This is 3D point cloud images are there. See, and remember, beautiful thing is there, interesting thing is there that how this 3D point cloud contains the information of the person. So this is converted into a 2D point cloud. See, another thing into a 2D point cloud, as you have seen that our colored image, basically RGB image is converted into a grayscale image. It is a similar operation that we are doing here. So once it is there and then you are able to, so raw data for each object was used to generate 3D point. A top view filtering technique was then applied to convert the 3D point cloud data into a 2D point cloud. There are two views. Again, remember you can take the top view as well as the front view, and again you can go to the processing for the accuracy. In our cases, we find out that the top view was giving better accuracy. That's why we are showing the top view. Otherwise, we have taken both the views. Project on the XY plane, effectively removing the Z coordinate. Which coordinate is missing? Basically, that is Z coordinate. So this projection creates a 2D representation that retains the spatial distribution of objects in the horizontal plane. Main advantage of this technique is easier visualization and analysis, especially for distant object detection. Remember, but here you should be very clear that distant means yes, it's a within a range, within a very few range only where MM wave radar works. right? So it is particularly useful in autonomous systems such as self-driving vehicles, drones and robotics, where fast and reliable object identification is essential. So here we any question till this part. So we are on the. I think those students who are asking the question, they can be given advantage, extra marks in the quiz, in the evaluation, because they are overall attentive. So that way, if I consider Suman, Suman Paria, Suman Krishna, only some may be given bonus mark. So others can also score the bonus mark. So here we take up a break, small break, see, right? So that you can think about the content. Remember, in the quiz part, whatever portion till tomorrow, even only the slides which we have shared, only that portion is there. Okay, we take up a break, and I hope that you would come back with the new question, interesting question.